Welcome to this third class about direct policy search and reinforcement learning. In this class, we will have a closer look at policy gradient updates to better understand their properties and limitations. So first, a reminder about policy gradient updates. You have some policy P theta. With this policy, you perform a set of trajectories. Here we sample m such trajectories. Then you compute this complicated mathematical expression that we will go into later. By the way, if the reward of all this trajectory is 0, this whole term is 0, so your gradient is null and your agent does not learn anything. And once you have collected all these trajectories, then you can compute this gradient of the performance with respect to the parameters, and you can update the parameters using some gradient descent formula like this one, or something more advanced if you use, for instance, Adam. And then you do it again, so it gives you a new policy P theta prime. You collect the trajectories again with this policy P theta prime. You compute this quantity, and you apply the gradient again, and so on and so on. That's how it works. Now let's have a look at more details. So first, we will focus on computing this quantity for some state action pair, for instance this one. We consider a Gaussian stochastic policy with state-dependent variance. So here you have the Gaussian output of our policy. So it's parameterized with a center mu and a variance sigma. And you have two neurons that output mu and sigma, and you give the state as input, and it provides you with a probability of actions in the space of possible continuous actions. Now, if a pair ST80 was rewarded with a large positive reward, we want to update the parameters theta of our network to increase the probability of taking the same action in the same state again. So what we do is that we feed the state to the input. It provides some values for mu and sigma. We compute the log probability of the action given the Gaussian parameterized by mu and sigma, and we change theta to increase this. So let's now have a look in more details at how to do this specific operation. So how do we increase the log probability of the action given the state for some state action pair? Again, the probability of some action AT is given by a Gaussian with this center and this variance. We want to increase this by changing the theta parameters. So we will do so by minimizing the loss in theta minus the log probability of the action given the state, as represented by the policy. To do this, we have to compute the probability of the action given the Gaussian function. In more mathematical detail, the probability of this action is given by the following function, and since it is the Gaussian, it can be written this way, and that's an exponential function. So if you take the log of the probability, the log of the exponential cancel each other, and you get this expression. So you can see that the log of the probability is in fact a quadratic function. So what we want to do is to increase the log probability of the action given the state, which means that for the given mu that we get, we want mu to move closer to the action where the quadratic function is the highest. So the gradient is with respect to these parameters, and then once we have computed this gradient, it is backpropagated to update theta. By the way, I have given to you the mathematical formula A, but in practice, you are doing this backpropagation with PyTorch or your favorite gradient computation library. So you don't have to care about this mathematics. This is done for you by the library itself. A word to say now that here I have shown you what happens if you consider just a function of mu. So we considered a fixed variance sigma. But by the way, there is another option to increase the probability of the action given the state, which is by changing sigma. If we decrease the variance, the probability of the action will get higher. In general, when the action is close to the center of the Gaussian, just by decreasing the variance, you will increase the probability to perform that particular action. But the point is that your policy will be more deterministic. And experimentally, if you try what I have described, you will see that decreasing the variance has more impact than increasing the center This is why we need entropy regularization, because otherwise the simplest solution for the neural network to adapt so as to increase this probability is to decrease the variance. Okay, this was how we compute the log probability for a particular state action pair. Now let's move to a different action pair. First, we have to figure out that the previous update moved the parameters theta in some direction depending on the probability of the action and the state. Now we do this for another state action pair, and the new update will be added to the update performed before. And the point is that this new update will move the vector of parameters theta in some other directions. So these two gradient states interact with each other. They may cancel each other or increase each other. Now, if we have a look at what happens with the whole formula, in fact, we are doing this gradient step for each state action pair that we have collected along our set of trajectories. So we have m times the horizon such state action pairs, and we are performing sums. So we are changing the weights of the neurons for one pair, and then for another one, and then for another one, etc., etc. So the gradient of the reward will be the mean sum over all the small gradients corresponding to each state action pair. By the way, since this is a sum, of course, the order by which we sum all these things does not matter. Actually, we can do this in parallel with a GPU. And if we want to speed up this calculation, we can even take several mini batches among our trajectories rather than perform a complete calculation from all the dataset once and for all. But if we use mini batches, it will introduce further variance in the applied updates. But the main point is that each update is local, but the sum of updates can result in gradient cancelling each other, for instance. Okay, some updates can contradict each other, so performing this sum of updates will work just on average. Actually, if the neurons at the lower level could make so that each gradient step only applies to a particular neuron to account for a particular state action pair, then the gradients would not interact with each other. We could have a single change for each neuron depending on just one state action pair. If this is the case, then the different gradients cannot cancel each other, and we have something that works perfectly. You might have such a situation, for instance, if you use a one-hot coding of the states. So it's interesting, and I'm not sure this has been studied in detail, to figure out whether when we are performing reinforcement learning on a neural network, there is a natural drive in the backpropagation to obtain disentangled update so that the gradient tend not to cancel each other. And the topic behind having separate representation for the different states and actions so that the different updates do not contradict each other is related a lot to state representation learning, and you have a survey about state representation learning here. So to conclude this short video about local gradient updates, you have to understand that we sampled many trajectory for a single policy, but a policy corresponds to a point in the landscape of the return given the parameters. Okay, that's some point here. By performing the updates, we change the probability of actions locally in each state, but doing this changes the value of theta globally. So we move to another point somewhere in the landscape. In general, if the gradient update is correct, we will move to a better policy, but this might not be the case. Even with perfect sampling, due to the interaction between the updates and due to the variance of the process, the sum of our local gradient steps does not guarantee moving to a better policy. And that's important to figure this out, and that will be the conclusion of this short video. Thank you for listening, and don't hesitate if you have any question.